I have been good with getting everything to YouTube though, that I have to say. Okay, folks, we are in week 7 of quantum field theory. Today will be our first day of QED. So QED is arguably the most tested theory. Not arguably, it is the most tested, accurately tested theory in the history of mankind. And what you'll find is really going from QED, going from scalar field theory to QED is not a huge jump. There are a few subtle issues we need to take care of because of this issue with antiparticles, but really the propagator takes care of that. And what we'll find is we can develop a very smooth algorithm which allows us to take any amplitude, write it as a sum of traces, basically, of the gamma matrices. And using all of the Feynman tricks for traces, it becomes a very simple procedure to get a final answer. And obviously the goal is to compute differential cross sections, which I hope you watched that video. I don't know if it was helpful. I certainly did not watch the whole thing. It looked helpful. So that's the goal, to compute d sigma over d omega. So you have some homework. Where's my chalk? You have some homework. You have Lancaster and Blundell, chapter 40, 13, and 14. So chapter 40 will be about very famous scatterings in QED, Compton scattering, Rutherford scattering, all of that. And chapter 13 and 14 will tell you about gauge theory. What is a gauge theory? What is a gauge field? I will not really spend time doing that here. We need to pick a gauge in QED. I'm not going to really go into depth. So if you feel like you're not comfortable with gauge theory, which I assume you're not, I would read these 2 chapters. They kind of go very slow. Like, what is a gauge? What is a gauge theory? You know, things that are not included in any other, certainly not in my QFT books. So I kind of like that they had that chapter. And in fact, one of the sections is called QED is the simplest gauge theory, which it is. It's actually not a bad way to be introduced to the subject. And really the way to think about it is scalar field theory. The particles were described very simply with scalars. QED is technically a vector field theory, okay? We describe photons with vector fields or vector potentials, right? These A mu's, right? Because photons have polarization. They have a vector direction. So you have to add extra degrees of freedom. So it just gets a little complicated. Also, I have some news. I got into graduate school. So I got into Princeton. So I'm excited about that. So unfortunately, I don't want to go to New Jersey, but I guess that's what's going to have to happen. So hopefully there's not going to be less snow. That's the problem. So, and then during the break, we'll talk about the research group. I want to talk about the structure of that. I kind of wrote a long email, but you know. Okay, any questions from last week before we start?
I think we read chapter 40 last week, or at least
yeah.
I wrote it down and read it.
Okay, good. Okay, then you're even more prepared. Then you know all the gamma trace tricks.
Okay.
Right? Is that what you did in 40?
Yeah.
Okay, good. Then actually today will look very familiar to you.
Cool.
Yeah. Okay, good. But you know, certainly read 13 and 14 because I took a glance at it and it looks very good. It really takes you through the motivation for using a gauge. We'll talk about it, but I'm not going to go into the depth of the textbook. That textbook, it's little. Okay, so I think we should just start off by writing the Feynman rules. I think that's the best way to start off. you could derive the rules in a very similar way. There are certain motivations we'll talk about, but let's just start off with the Feynman rules. So we have an interaction Hamiltonian in QED, which now looks okay. It looks pretty much like something we would work with. It should look very familiar to Yukawa theory, except for the fact that now instead of a coupling G, you have a coupling E, the electric charge. And now you have the coupling to the gauge field, A mu, okay, instead of a coupling to phi, right? So in Yukawa theory is like scalar QED, right? Because you have G psi bar. I'll just write it down. So in Yukawa theory, you had G psi bar phi psi. So you had a coupling to G, and you had a coupling to a scalar field, right? The scalar field was the virtual particle. Now, notice how our coupling changes to this vector kind of quantity, and A mu is called the gauge field, and the gauge field describes the photon stuff. Okay, we have a vertex factor. So the vertex factor is minus IE gamma mu. Okay, we have a propagator for all internal photon lines. The reason we have remember G mu nu is eta mu nu, right? It's not some arbitrary metric. The reason we have the Minkowski metric here is basically to make sure the sign comes out right, because as you know now, antiparticles will have the opposite sign of regular particles, and G00 has the nice function that it's equal to -1. So we can use that to our advantage. Not only that, G mu nu will contract a lot of the times with the gamma matrices in computing amplitudes to give scalars, right? Because eventually we want these gamma matrices to get out of the story, right? They're kind of just there. We give them some configuration and we're done with them. So that's why G mu nu is there. And actually, we're going to talk a lot more about the form of this propagator and how it's different from a scalar theory to a vector theory to a tensor theory. Okay, if we have the gauge field acting on a state for one particle with momentum p, we can now say that this guy has some polarization, E mu of p, right? And I can represent this now. What this really represents is an external photon line, right? This is an external photon line, not an internal one, because it's just some photon with some polarization. Similarly, if it's acting on the out state, if I have that gauge field, I get a polarization epsilon mu star of p. And that's the same thing, it's just propagating in the opposite direction for an exterior line. Okay, these are basically the rules. And of course we have spinors, right, for fermions, which we had in Yukawa theory, right? In Yukawa theory we had spinors. Only difference between Yukawa theory and QED is the interaction particle. That's it, and the coupling. But the coupling, who cares? The coupling's a number. I changed the coupling based on the theory. And we will also work in a gauge. We'll work in Lorentz gauge. That will be the gauge we work in for our calculations. You know, there's all kinds of gauges you can work in. Feynman gauge. That's that the second derivative of the gauge field vanishes. That's basic. I think you've seen this, right, Jenna, in that chapter? They must have picked a gauge before they started doing calculations, or.
I don't really remember it, but I'm probably just not remembering it.
Okay, not that it really, definitely in chapter 14, they'll go into it. But, you know, just make sure you look out for this guy. You know, practically it doesn't really matter. it's just imposing some constraints when we start explicitly computing things. Okay, now the natural thing to do would be to write a mode expansion, right? That would be the natural thing to do. So let's do that. Let's write out the mode expansion. So we're going to write out a mode expansion for the gauge field, A mu of x. And naturally, what you should expect are creation annihilation operators and polarization vectors. 1 over 2 EP. Okay, now we're going to write out our whole expression with creation operators, annihilation operators, polarization vectors. So I have some APR with some spinor index, epsilon mu R of P, e to the minus I, e dot x, plus a dagger R, we'll call it P prime, epsilon mu R prime star, P prime, e to the I, P dot x. And that gives me the mode expansion. And really, I don't need a prime because these R's are just labeling some, right? I should put this summation in here. Sorry. Just add the summation, right? So we have R going from 0 to 3, right? So R is like the index. Like what component am I working with? T, X, Y, or Z, or whatever. That should go up there, really. That's why I don't need an R prime. So for example, if I have a photon with momentum P along the z-axis, I can write down its polarization vector, and it takes this form. T component doesn't care. Since I'm along the z-axis, it doesn't care. And the 1 and 2 axes will change. Similarly, if I want a polarization vector along the x-axis, it's pretty easy to just kind of construct one. And if I want one along the 2-axis, again, it's straightforward to kind of see how I would construct one. Okay. One of the benefits about the photon is it is massless. So that will help our calculations somewhat. It's also spin 1. Okay, another way I might want to parameterize my vertex factor, this is a common way of writing it, is minus I Q E gamma mu. So we call the vertex factor some function of the charge Q. That's another way people write it. Okay, so let's compute our first amplitude, QED amplitude. Not really Q. Okay, what are we really building up to? We're building up to E plus E minus to mu plus mu minus, which is what the very first thing we started the course with, right? So that's what we're building up to. That's the classic QED amplitude. But let's do some warm up. Let's do some like jogging a little bit before we get to the big stuff. So let's do an amplitude where I have 2 fermions coming in, exchanging a photon, and 2 fermions going out. No antiparticles, nothing. And let's see what happens. But hopefully you can see why we motivated this with Yukawa theory, because it does help. Okay, so I'm computing some amplitude. Okay, and I have some Feynman diagram that looks like this. 2 guys are going in, exchanging a photon, and going out. Okay, and we'll say this has momentum P, P prime, K, and K prime. Okay, very simple. I'm going to have 2 couplings. So I'm going to get, first of all, I'm immediately going to get a minus IE squared out front. Right, that just comes from the two vertices. You know, I should really write this here. It's the whole thing squared, not just the E. Okay, then I have an outgoing particle with momentum P prime. That gets a gamma mu. And I have an ingoing particle with momentum P. I have one propagator. I'm dropping the I epsilon. It's not important. And then I have another outgoing particle, no antiparticles, with momentum K prime, another gamma matrix, and UK. That's my amplitude. That's the basic amplitude. Okay, and we can say that Q squared is equal to P prime minus P squared. Okay, that's Q squared. Because remember, when you're really writing down these amplitudes, and I hope Lancaster-Blundell said this, you should start from the left, right? Work out each process kind of like in order and go to the right. That's how you should do it. So notice how I went in order. Started with U of P prime. I went down. Well, I didn't. I should be a little less stringent because I took out the vertex factors, right? I took out the minus IE squared, but I did leave the gamma mu, right? Then I put my second spinner. Then I put the propagator. Then I put U of K prime. Then I put the second vertex, even though I moved that outside. And then I moved this, right? Okay, so this is the basic amplitude. Now, it often helps, and I think you guys have started to realize this. We usually pick a limit to work with. We don't just like, this is not a very useful form to do any physics in. One thing you should notice that this G mu nu is going to do some nice things with the gammas, right? It's gonna contract in a nice way, depending on obviously the construction of the gammas, what component I'm working with. But for this example, we'll work in the non-relativistic limit. So things are moving really, really, really slow. That's what I mean when I say non-relativistic limit. And I think Lancaster-Blundell do a very good job of really working in all of these kinds of limits, like the very hyper-relativistic limit, they actually show you what happens. I'm going to do non-relativistic, and that means I can basically work in the time components of everything. Okay, I'm just looking at the G00 component, gamma 0 component of everything. I'm not looking at any spatial components. Okay, and recall that the combination U bar of P prime, gamma 0 U of P, gives you this combination when you multiply it out. This is something we've seen before in the non-relativistic limit, because I'm looking at the 0th component, just gives you some 2m with our spinners, right? Where these are two component guys. Okay, so we've seen that before. And so if I just use the non-relativistic limit, then my amplitude, let me just do it really quick in my head. So I get a plus IE squared from the square over P minus P prime squared. So that takes care of all of the propagator stuff. The gamma matrices are obviously going to disappear because they've been contracted. And I get a 2m C dagger P times a 2m dagger K. These are just this is just the spinner degrees of freedom. These are just basically numbers, really. It's not really, I mean, you can compute the number. We don't really care. And of course, this is all dotted with the time component of the metric, P00. And that gives me the amplitude in the non-relativistic limit, right? Because this combination gets rid of the gamma matrices. They just come out, right? I'm left with the G00 component of the metric. I pulled this guy, I squared it, so that becomes a plus I. And I pulled this denominator of the momentum out front into this factor. Okay, so it's just some algebra. Okay, so let's dot this with G00. Okay. I hope it's obvious what dotting this with G00 would have. You just get it's just basically multiplying this thing by -1, right? That's it, because G00 is -1. So this top thing becomes a minus in the numerator. So let's just dot it. So I mu now becomes minus I e squared over a minus p prime squared. And then I have my spinor stuff. I'll just call it my spinor stuff now. Okay. And that becomes the amplitude. Or I don't even know why I gave this a minus. That takes care of it. That takes care of the situation. So this should look very familiar to you. So recall, a Coulomb potential takes this form. Alpha over R. So recall in Yukawa theory, we derived a potential. So this is a Coulomb potential. Hopefully this kind of looks familiar to you from past experiences. And recall in Yukawa theory, you derived a potential in quantum mechanics. You looked at a Yukawa potential and you derived it from a scattering problem, right? You solved a scattering problem. And in scalar QED, in the non-relativistic limit, you can do this calculation yourself. You would get something that looks like this. You would get p prime minus p squared, plus m phi, right? You get this mass. Notice how I don't have any mass in the propagator for QED because it's massless, right? So we don't worry about that in QED. And then you get the normalized stuff in Yukawa theory. So let's take a look now. Let's kind of analyze what we derived here. So first thing to note, it kind of looks like a Coulomb potential with an e squared up top and some distance squared. So it's kind of like a 1 over r squared thing going on. And something to kind of think about is in the Yukawa potential, wait a second. Yes, in the Yukawa potential, no, I did it right. Sometimes you have to check if you derive the right answer. In the Yukawa potential, I have a overall positive sign. So I'm not, okay, first of all, this stuff is just garbage, okay? It's just some number. I'm really concerned about this in the non-relativistic limit. This is telling me about the physics. I have a potential, and in the Yukawa potential, I see that this overall sign is a positive. That means that this is an attractive potential. Which is what we expect in Yukawa theory, right? In Yukawa theory, the particles have no charge. They're attractive, okay? They're attractive. In this theory, where I just have fermions and no antiparticles, I get a repulsive potential. There's a minus sign out there. Oh, that makes sense. Why? Because repulsive. In the vector theory, in QED, particles have charge. What particles have the opposite charge? Antiparticles have opposite charge, right? From their normal particle. I put no antiparticles here. So I should expect an overall minus sign out in front. Okay, so QFT tells me the right force going on. Again, this is the non-relativistic limit. I haven't derived any cross-section or anything yet. And you guys should be going, yeah, it is the non-relativistic limit. Why? Because we pulled out a Yukawa potential in quantum mechanics, non-relativistic quantum mechanics, that looked like this, right? And you had a problem on your homework, and Gabe showed you how to derive the Yukawa potential just using the Born approximation, right? So basically, you should be going, yeah, this makes sense. We're not working in that relativistic regime yet. We will be in 5 minutes, but not yet. We're warming up using some of the apparatus from QFT. Okay, now you should do this exercise on your own. So now let's say I have the Feynman diagram where I have the exchange of a photon, but now instead, I have a particle and antiparticle going in. And I have a particle and antiparticle going out. Right now the flow of momentum is flipped and everything. Now if you compute this amplitude, and please verify this, label them some momenta for the antiparticle and particle, you'll find that you get the same potential out in front, except now you get a -1 times minus p squared over p minus p prime squared. So this -1 that you get out in front, and this makes sense because now you have antiparticles and all that does is changes the sign. And you'll find that now this becomes an attractive potential because now you have an overall positive. So attractive potential. Okay, which makes sense. They're opposite charge. And we've heard the saying opposites attract. QFT says yes, they do indeed. So this is a nice little exercise to kind of get the physical right, and you would need, remember, you would need this identity, that V bar of some momentum K, gamma 0, V of K prime equals plus 2m, spinner stuff. Okay. If you work that out, you'll get it's attractive. Okay, so we did our first little exercise. We did our first little exercise in QED, right? Where now we've kind of seen that it's right. It gives us the right stuff. So before we move on to the big show, E plus E minus, I want to talk a little bit about the kinds of theories we've constructed. So we've looked at Euclid theory. Euclid theory is a scalar theory with a coupling G psi bar phi psi. If I have a particle or antiparticle, it is indeed attractive. And also if I have a particle and one antiparticle, it is indeed attractive. So it's attractive in all scenarios, right? Because there's no distinction in Euclid theory, right? That's a scalar theory. Then we're learning about QED. QED is a vector theory, right? We're coupling to a gauge field. So we have E psi bar, gamma mu, psi a mu. And if I have F and F, two particles or two antiparticles, identical particles, it's repulsive now. And if I have one particle and one antiparticle, it's attractive, right? And now what's the last step? We want a tensor theory. What's a tensor theory technically? It's a quantum gravity theory. So let's just kind of take a look. These are spin 0. Okay, these are spin 0. These are spin 1. Wow, I have one index. Wow, okay, that's kind of interesting. These are, and a gravity theory would be spin 2. That's like the natural thing to say. And you have a tensor theory. And again, hopefully it's clear that in all situations, it would be attractive, right? Repulsive gravity is not really, it is a thing, but it's very subtle. So it's really pretty much just attractive everywhere. And I'll write down the propagator for gravity. In fact, for your research group, you guys are going to compute a gravity amplitude. You can do it. It just doesn't mean much in the grand scheme because we don't know if a graviton exists. So you could do it, but it just doesn't mean much. It's not like some secret thing. I think I've told you the story, right? One day Feynman came into the office at Caltech and Murray Gell-Mann asked him, okay, what are you going to do today, Feynman? And Feynman says, oh, I'm going to quantize gravity. Right? Because technically speaking, it's just kind of the same. If you're thinking about it from the perspective of quantum field theory, it's not, you have a lot of problems, which we've discussed at some length. Okay, so let's just write out the graviton propagator just for fun. You would have some mu and rho sigma, and it's right. You would have 4 degrees of freedom now to take care of the graviton. You'd have a 1/2 minus g mu rho. It's pretty nasty, I gotta say. Minus g mu sigma. Right now, I just have to contract with pretty much everything I've got out here. G mu sigma, G mu rho. That's it. That's the propagator times an I q squared plus I epsilon. And if you just recall that minus G00 squared equals 1, when you do your calculation, you'll see it all works. Notice again, I've got this same guy out here, and what's really changing is what's out in front. And obviously there's a different vertex factor and different stuff, which I'll give you in your research document for next week. And don't worry, I won't make you do loops because you can't. Okay, so that's gravity. Now that's all we'll talk about gravity in this class. That's as far as we'll get. I'll just write down the propagator and we're done. If we will eventually do quantum gravity in like 6 more months, but we'll get there. We'll get there. Okay. Okay, let's get to the big show now. This is it. This is what we started the class with. The famous E plus, E minus to mu plus, mu minus. Another variation of this scattering that they see in the lab is when 2 electrons actually go to 2 quarks. That happens too sometimes, which is kind of crazy. But we'll talk about that when we get to QCD. Okay, now really, we can write down the amplitude now, I hope, like in a second. Now you should basically, oh, I can write down an amplitude just by staring at the Feynman diagram. That's good. But as you know, especially Jenna, because you've read chapter 40, getting from this kind of abstract amplitude to a cross section is kind of an art. It's kind of not an easy thing. It's not trivial, certainly not trivial. So I'm going to take you through the steps for this process. Basically, the algorithm reduces to getting the amplitude as just a sum of traces. And I'm going to write down probably 30 trace rules. You know, I have a little notebook with all the equations, just the equations listed. The gamma trace rules are in there. So, you know, you use them all the time because it helps you simplify calculations. So anyways, let's draw the Feynman diagram. Also, those of you that have read chapter 40, you will notice that they describe different channels, S channel, T channel, U channel. We'll get there. We'll get there. Don't worry about that yet. That has to do with these things called Mandelstam variables, which we'll describe. I don't use them that much, but they're kind of outdated. So of course, the photon has some momentum q. I have a particle going in and an antiparticle going in, right, into this vertex. So this is E minus with momentum p. This is E plus with momentum p prime. This guy's going out. This is the antiparticle. So this is mu plus with momentum k prime. This is mu minus with momentum k. Okay, that's the basic idea. So can someone tell me the amplitude? Give it a minute, work it out, and then just tell me the amplitude. So what is I am? When you're ready, let me know. Now we have antiparticles, right? So we have to be careful. And now also remember your spinners are going to need a spinner index. So if you have some spinner V, it will need like an S of whatever the momentum is. It's going to need some spinner index. Just pick a random letter. I don't care. I won't use your letter. I'll use the letter I want. Give it another minute. Don't look at your notes from the first day of class because it's the same thing. Because we did this the first day. That's the funny part. That's why I told my friend I'm teaching this. And you know, it's always interesting to hear how the people's process for teaching, because QFT is so variable and everyone does it differently. I was like, yeah, I'm going to show them QED amplitude the first class. They're like, what? I'm like, yeah, you should just see like what's going on. And now hopefully you have a much better understanding of what's actually happening. And obviously we're going to work through it carefully. Okay, does someone want to take me through it? It's okay if it's not right, I don't care. That's the fun of doing this. No one's getting a grade. All right, let's go. What do we got?
I got IM equals IE squared, U bar of K times gamma mu.
Okay, wait, we
U
have
of
to go
P.
slow because I don't have it either.
Oh, okay.
So
Yeah.
let's just start with this guy.
Okay.
So you have a particle. Let's start with the antiparticle. So what spinner am I going to write for the antiparticle?
Oh, I didn't get that far. I just wrote the first line.
Okay, what'd you write? What'd you write?
Oh, well, if you're starting with the antiparticle, then U bar of K prime.
Good, but it's an anti, so we label it with a V, right?
Oh, VV, right.
So V bar of P prime, right? Because I'm starting with this positron. And I just, you know, they're just labels.
Okay.
And I'm going to need some spinner index. That's the only thing. I'll just call it S prime. Okay, so now we make our way this way. Now I'm at the vertex. So what do I have to add there?
Gamma mu.
Yeah, really minus IE. Gamma. You moved all the minus IEs out front and put minus IE squared, right? That's fine.
Yeah.
Yeah. Okay, now we work here. So now what am I going to put for the electron?
U bar. Is the spinner part just S?
No bar because it's ingoing, right? So it's tricky, right? Because with antiparticles, it's opposite. When it's ingoing, we write it as an outgoing, but this is an ingoing, so it's just a U.
Right. Okay.
And we'll put the spinner S, and then we'll call the momentum P, right?
Okay.
Okay, now what do I need for the internal line?
Propagator IG mu nu over Q squared.
And we'll write the full momentum. So we'll write P prime minus P squared. We'll just write it at that vertex.
Okay.
Okay. Or let's write Q squared for now. It doesn't even matter, honestly. Okay, now we work our way this way. And now I am going to start with this. So what do I put?
U bar.
Yep, U bar.
U bar S of K.
We'll call it R because we'll have a separate thing for the muons.
Okay.
And then I need another vertex factor, right?
Mm-hmm.
But remember, I need a different gamma index, so it contracts. And then what do I put for the outgoing anti-muon?
V.
We'll say R prime.
Yeah, R prime of K prime.
Yeah, good. That's it. That's the amplitude. It's not so bad, right? I just have my own order, but it doesn't even matter. And now the question, now this is what we wrote down the first day of class. We used very heuristic arguments to come up with some amplitude. I used kinematics arguments. We got pretty close, I told you. Now we're actually going to use the trace technology, which I kind of alluded to first lecture. Okay, so the very first thing I'm going to do is I'm going to put this in a better form. I'm going to actually contract the gamma matrices. I'm going to do that whole business, and it's a very simple calculation. So the amplitude from E minus to P, E plus P prime, ingoing, out, mu minus K, mu plus K prime. Okay, gives you what? Now I'm really going to get rid of my propagator. What do I want to pull out? I squared over Q squared, just pulling out all those factors. V bar of P prime. Now I can get rid of these like spinor indices because I'm going to contract gamma mu U of P. It's my first bit. U bar of K, gamma mu V of K prime. Okay, so that's how I simplify the amplitude. That's my first. I'm going to rewrite it up top. Okay. I assume you've seen that manipulation before, right? Okay, now obviously, what do I need in the cross section? I need m squared, right? That's what I want. That's the whole point. By the way, did you guys watch the Dotson video? Did it help or? Yes? What did he say? What did he go through? Quick before we go through into this.
He started with like an example to like get a better understanding of what just like straight up what a cross section is, like classically, I guess. And then he did and then he did it. He did a cross section.
Okay, that's good. No, that's good.
Yeah.
Okay, so we need m squared, and I'm going to use a nice identity. And the identity I'm going to use is that V bar. Let me make sure I think this through. V bar gamma mu U star equals U gamma mu V. Now U bar. Okay, so I'm going to use that identity. And if you use that, you can get mu squared, m squared easily. Let me compute it. I get e to the fourth, q to the fourth. See what I want to do. Yes. V bar of p prime, gamma mu, u bar of p, k. What was my momentum? Who cares? I'm just gonna do it this way. U bar of P prime, gamma mu. What am I missing? V of P. Okay, that gives me M squared. Again, no, that does not give me M squared. Wait a second. I can't be so loose. Hold on. I need this whole argument again for the antiparticles. So let me just do this clearly in my head before we go to the antis. This needs a prime, obviously. And now I'm just using that identity. That's why it's going to look weird. And then I get the same thing for the k's. So U bar of k, gamma mu. Yes. V of k, V bar of k prime, gamma mu, U of k prime, k prime. Okay, that's what I get. Or just k. You know, it gets really confusing with all the labels. Honestly, that's the most confusing bit. It's not even the algebra. Okay, this is just squaring it, right? That's why I have two sets of p's, two sets of k. I'm just squaring it out. That's all I'm doing. So don't get alarmed. Don't be like, why are there two k's and two k primes? It's because I'm literally squaring it. I'm just putting it in some weird ordering because of my identity. Hopefully you can figure it out after. Horace Johnson. Okay, now we probably know, we should know that as we manipulate this, obviously this is so different than the argument I made in week 1, which was just like logic argument. But you know, these are very useful techniques that I'm going to show you. We know that in the lab, we take an average of sums, an average of spins. We have to sum over the spins, right? So that will be our next step. We're going to do some process where we sum over all the spins. So I have S prime, R prime. And now we're going to have to sum over all of that. So I had an SS prime go to an R prime squared. So now I'm going to have to work out this spin sum. And if you recall from our discussion, a sum over, if I have the spin S, a sum over the U spinners gives me P slash plus M. And similarly, a sum gives me a P slash minus M. Right? This is just a basic thing that if you need review on, go into Lancaster-Blundell. I think they do show this, right? So this expression for spinners. Yeah. So, you know, let's use that. Let's use those kind of rules and let's complete the spin sum over this kind of massaged amplitude. I'll just write it up top. Right, and I'll just remind you that the Feynman slash notation is just, this is just saying d mu gamma mu, right? Or this is really saying P slash is just d mu p mu, right? And we need a gamma. That's the slash notation. So now we have to do our spin sum, which is kind of annoying, but alas, the experimenters, that's the way it is in the lab. So if I take the sum from two spins, right? Because now we're going to have two spins for our spinners. I get some V bar, S prime. I'm going to have another index A. You'll see why in a second. What A labels of P prime, gamma mu AB. So now I'm just taking the amplitude I just showed you, the squared amplitude. USB. I have to go very slow. I'm sorry. Mu V S prime of D. Okay, this is the first piece of the amplitude, of P prime. This is the first piece of the squared amplitude, right? And now notice what I've done to it. I just added spin labels on everything, A, B, C, and D. And I'm saying I'm going to sum over those spins. That's all I've done. Make sense? Remember, I had terms with K's in them too. I'm not going to do this for the K. I'm just doing it for the first term, so it's not a mess. You can repeat the argument. Okay, and now using what I just wrote down up top, I get the following expression, P slash minus M. Let me make sure I get my indices right. dA gamma mu AB. Now I'm going to get another slash naturally. This time it's a plus CD. Don't worry about the letters are just, BC gamma mu CB. There we go. Okay, so now I've taken these identities for the spin sums, which you've derived before. And I've come up with this. This is a long massage. I highly recommend you do this on your own or together when you get together, because it's important. You want to make sure you can calculate. Do it your own way. You don't have to do it my way. Do it your own way. I use very random, specific notation. And now, here's the fun part. I can write this now as a bunch of traces. It is not obvious how, but it will be. So I can actually write this now as a trace. I'll explain why. Minus M, my first term, gamma mu, P slash plus M, gamma mu. That's it. We've achieved it. We've done it. We've made it, because you guys should be going, that's a really simple thing to evaluate. Do we all know what a trace of a matrix is? Okay, it's just adding the diagonals. All right, so like if I have a matrix A, B, C, D, the trace of this guy is just A plus D. You just add the diagonals. And this has a gamma matrix. This is P slash, right? So this is, I wrote P slash wrong. I'm sorry. P slash is gamma mu, P mu. Sorry, I wrote like D mu. I don't even know what I was doing. I was in some alternate universe. That's P slash. So now I have two gamma matrices. I just have to take the traces and I get the sum of the spins. Okay. Beautiful. Now I did this for the electron stuff in M squared. Now I'll just write down what you get for the muon stuff, but do the calculation on your own. And let's write down the full amplitude. It's really not that bad. It looks bad. It's really not that bad. It's just squaring things and doing some algebra. Okay, so let's write down the full amplitude. I have some normalization of a factor of 4. The sum of all the spins, m squared, equals e to the 4th, 4q to the 4th. This is just my vertex factors. Should write trace out front. Trace p slash minus m me, we'll say this is the electron mass gamma mu. All right. We'll just call it the electron mass p slash plus me gamma nu. Oh, I'm sorry, my notation's very sloppy today. Gamma nu times the trace. Now I'm going to do it. It's literally the same thing, except I'm going to use the muon mass gamma mu p slash plus m mu gamma mu. Okay, we have gotten this into some nice, pretty expression. And now, really, the algorithm says you can do this to any QED amplitude, unless it has a loop, which is what we're going to do next week. Radiative corrections. Johnson is actually, remember last week I told you that I showed you a loop diagram and I said this is really complicated and you get a divergence. Johnson's going to do that today. He's going to show you how complicated it is. So you're going to see. He's going to go through the whole process. Okay, now how do we evaluate this? We need some trace rules, right? We need some tricks. So I'm going to give you a bunch of tricks which you could easily derive, but it's easier to list them. And then we'll take a break. So what time is it though? I feel like I'm going kind of slow today. 33. Yeah, let's take a 5-minute break till 36 or 37. Who cares? Okay, because we've gotten to the main punchline. So the goal, we will meet tomorrow at 9:30. I know I wrote 9:30 to 10:30. Most of the time I want to end by 10. I don't really want to go to 10:30. So yeah. So we'll probably end early. I don't want to stay too long. Really that half an hour is going to be for you guys to ask me what you want to ask me and what you're working on. Okay. And I know I wrote that I'd like the answers by Sunday. I would. So then we can move on. You know. I meant it. I meant the day. So these first 2 weeks are not going to be that hard. Hopefully. If they are, then we should talk. We can make it easier. That's the fun. I'm in no rush. I don't care. I honestly, I'll go at any pace you want me to go at. Really. I mean, I don't care. I'm doing the research I have to do. So it's more about what you guys are understanding. That's the idea. Oh, Bob, I don't even think you were in the chain. So we should talk because you should make an overleaf. So we should talk about that. But we'll see. I was telling Jenna, I'm a big Jeopardy fan, and Noether's theorem was on Jeopardy. But Jenna watches Jeopardy, so she saw it. So she stole my thunder. Yeah. So the goal, hopefully when Corona's done, this is my goal. I think it's going to be done by the summer. I'm very confident because I was reading some stuff in the morning. Cases are going really down now, thankfully, because of this vaccine. We don't know the side effect. Like my mom works in the healthcare. She works at a hospital. She got the vaccine. She didn't get symptoms, but who knows long term, but who cares? Get the vaccine. I don't want to sound stupid, but my goal in the fall is to get this group together in person. It's going to happen. It's going to happen. Mark my words. Oh no, Jenna's in California. What am I even saying? Never mind. Never mind. And Olha will be, never mind. I felt like all of you were in New York. That's okay. Okay, my goal is to sort of get us in person somehow at some point in life.
You'll Zoom in virtual person.
Sorry?
You'll Zoom in virtual person.
Yes, yes, indeed. Okay, let's continue. I thought you guys wanted a break, but you seem to be ready to go, so let's continue. Okay, so let's just kind of talk. So first of all, the first obvious trace rule is that the trace of a single gamma matrix is just 0. That should be obvious because there's no diagonal. So if you can interpret this. If you have an odd number of gamma matrices, you have 0 trace. Notice how in this expression, I have an even number of gamma matrices. I have 4 in this term and 4 in that term. Okay, now I'm just going to list a bunch of identities, which if you want to check, if you feel excited about gamma matrices, you can check them. So the trace of gamma mu, I can write it as the trace of gamma 5, gamma mu, gamma 5. Okay, I can write gamma 5 squared as equal to 1. Okay, the anti-commutator of gamma mu, gamma 5 is equal to 0. We remember what gamma 5 is, right? It's I, gamma 0, gamma 1, gamma 2, gamma 3. Gamma. It's like everything. It's like the Frankenstein gamma matrix. Okay, the trace, you know what? I'm just going to start writing them up top. There's a lot of them, so. The trace of gamma mu equals 8 g mu nu minus the trace gamma mu. You know, I like to think Feynman just sat there and started randomly coming, just playing around with this because it seems so stupid. It seems so arbitrary, but you use them so much in QED. Just memorize. It's the one thing I'll say. Don't even memorize them. Just write them on a list and look at them when you're calculating because it's just so easy rather than check them once. Do check them, like play around, check, see it all works. It's like, remember the first quantum field theory thing we did when we were doing quantum mechanics, conceptual, whatever. I wrote down a bunch of identities, right? But then I said, this is the only time I'm actually going to work it out, right? And I did, and we had the cinches and the cut, and it all worked out. As you can see, I'm never going to do that again. So, work it out on your own. Because like, imagine, now I have to write out all this. It's not happening. That's the beauty of tensor notation. Okay, let's get crazy. So we have the trace of gamma mu, gamma nu, gamma rho, gamma sigma. Hopefully you can kind of interpret where this is going. So I get a 4 g mu nu g rho sigma plus g mu rho g mu sigma plus g mu sigma g nu rho Okay. Similarly, recall, if I have the trace of the identity matrix, it's just equal to 4, right? Because I just have ones across the diagonal, right? Okay, if I have the trace of any odd number of gamma matrices, so odd number gammas is equal to 0. Trace of gamma mu is equal to 4 g mu nu. Just wrote out that long guy. Okay, trace of gamma mu, gamma nu, gamma rho, gamma sigma, gamma phi is equal to 4i times the totally antisymmetric tensor. Sorry, I think you need a minus sign out in front. Okay, gamma mu, the inner product gives you g mu nu. Gamma mu, right? This better makes sense because I've used this so many times in our amplitudes, right? This equation. So please check that. I can write this as some linear product, 1/2 g mu nu anti-commutator gamma mu. That's just equal to g mu nu downstairs, g mu nu upstairs, and we all know that that inner product equals 4. Okay, that's basically it. There's many more. I think the book lists all of them. So if you need a reference, just check that. Check any quantum field theory textbook, it will have it, not just that. I think this one is the most important that I've used, right? Because the propagator contracting with the 2 gamma matrices in the amplitude. Any questions? Okay, let's continue. Now we have the tools to evaluate those traces that I wrote out. Now I can just simply evaluate all of that. And let's write it down. So we have the trace of P / minus ME gamma mu P / plus ME gamma nu. All right, that was the first term. And I can write this now in the following way for P mu P prime nu. Let me just make sure I know this. P prime mu P mu. Right now I'm just pulling out all my momenta. Minus G mu nu P dot P prime plus ME squared. Okay, and this is just basic, algebra and manipulation of the rules, which you work out on your own and verify. Okay, now I can write down the trace of the muon term. in a very similar fashion, practically the identical fashion, except with lower indices. Okay, it's the same thing. Now, obviously, ME is equal to 0, not ME. Oh, yeah, let's do this. I make another approximation. Shocker, physicists making another approximation. I work in the limit where ME is much less than MU, which I can do. Okay, so I can ignore the ME squared term, which is reasonable, right? Because the mass of the electron is much, much less than the mass of the muon. So who cares about that? You'll start to realize this. We practically work in limits all the time. That's like life. You just what you do. You just knock out things. Oh, that's tiny. Bye-bye. You know, oh, I'm not really worried about that dependence in this equation. Okay, that's honestly, I'm saying it on camera. That's like half of the art of being a good physics student. It's like what limit to take and what to ignore. That's like what approximation to me. That's kind of like all of the art of doing physics. It's not really algebra. A lot of people do algebra. It's like, okay, and now I can finally write down the amplitude, sum over the spins with my silly 1/4. M squared. Oh God, I gotta. 8e to the 4th, q to the 4th, I think. P dot k, p prime dot k prime. Now I'm just, multiplying these two guys. Plus p dot k prime times p prime dot k plus m mu squared dot p prime, right? I'm just multiplying them out, and it's all dot products. Remember, these p's and k's have 4 components, right? That's why I'm not writing it out as a multiplication. It's always going to be a dot product because they're vectors, technically, in this space. This is p mu. This is k mu, right? They're not one number thing. And sorry, Emmy, you're out of there. I don't need you. Knock you out. Okay, now we're ready really to analyze the kinematics. Now we're really ready to start computing a cross section. That's the next natural step. We have m squared. And if you just take a look at this intuitively, you can say, oh, really, it's just a bunch of momentums dotted with each other. And it's going to give me some kind of kinematics. So now we have to pick a frame of reference to talk about the kinematics. Okay. And we use this kind of like as a blueprint. Really, the amplitude in the form m squared is really like a blueprint. It can't really give you a lot of physical stuff on its own. You have to, as I'm sure you've intuitively started to see. Okay, let's write out a frame of reference and let's write out the kinematics. I swear we'll get the answer we got the first day of class. Give it 10 more minutes. Okay, I'm gonna write this up top. So yeah, a quarter spins m squared Okay. So I'm going to work in this frame called the center mass frame. So I have my thing going on here. Something comes in, scatters at an angle, scatters. That's the basic picture, right? K prime is equal to E minus K, right? This is the energy component of the 4 momentum, right? And then this is just the 3 spatial bits. K equals EK positive. Okay. And here I'm just going to say that P is equal to E. I'm just going to parameterize this by the energy. That's all. No spatial bits. It's just going in and crashing. And this is along the 3-axis. Okay. That's my kinematic picture. It's interesting, right? Because in the S matrix formulation, you start all of your data at like very infinite time. So nothing's interacting. So these zygotes are coming in from infinite time. Okay, I impose my on-shell condition, which is just to say that K equals E plus M mu square root, or minus, right? We want them to be equal. And I also say that K dot Z hat is gonna have obviously to do with the angle I've scattered at. So I get K cosine theta, the angle. Okay, that means that Q squared is going to equal 4E squared. Why am I writing that? Because I'm really saying that Q squared is equal to P plus P prime squared. Right, so I'm taking that dot product. Because P dotted with P prime is equal to what? It's just equal to 2E squared. Right, forget about, if you just do out the multiplication. And now I can also even write down the dot products P dot K. Okay. P dot K equals P prime dot K prime equals E squared minus E K cosine theta. I'm just taking the dot product with the stuff I've, constructed, that's all. And then P dot K prime equals P prime dot K equals E squared plus EK cosine theta. Okay, but these are just dot products, that's all. Hopefully these are okay. Oh, you can't hear me? Really? Is it good now? What?
I can try rejoining.
How about now? No? Olha, can you hear me?
I can hear you fine.
Can you guys all hear me? Is it just Jenna?
Like
Oh,
maybe
Wait,
it's
what?
with connection because when I that connection, like I was thrown out, so I couldn't hear you.
I can hear you now. I
Oh,
think.
okay, good. Okay, good.
Yeah.
Okay, we're almost out of time. I'm gonna have to go over Johnson. Sorry. So these are just dot products, right? That's what I was saying. I hope that's okay, right? So now you are probably going, oh, this is great. I have the dot products from the kinematics, and that's basically all the terms in the amplitude. Now I just have to plug in chug. So let's do that. Shall we do that? Let's plug in chug into the amplitude. You could have set up the kinematics any way you wanted. If you wanted to do this collision with the x along the one axis, the x-axis, or the two axis, the y-axis, you would have a different structure of the angles and everything. That's all. It's not really a big deal. And so now when I plug in all my dot products in the center of mass frame, I get a very simple expression. I get e to the fourth, 1 plus mu squared over 2. Obviously, I'm going to be doing a lot more algebraic sorry, this should be an e squared. A lot more algebraic manipulation. Which you should do on your own. All the pieces are there. What am I? Oh wow! I can't even cosine squared theta. Okay. Squaring the cosines. That just comes from plugging in all the dot products and rearranging things with some algebra. Okay, and I can now get a cross section d sigma d omega. That's the key. As alpha squared over 4 ECM squared. Because remember, we have like some 64 pi. We have like a lot of random terms in that. 1 minus m u squared over e squared square root. And I'll call this piece rho times rho. This whole 1, 2, 3 terms. So I don't have to rewrite it. And from that, you can get sigma total. You can get everything. Okay, you can get the full cross section. Hopefully this expression means something more to you now that you've seen Andrew Dotson's video. By the way, this matches experiment like 90%, all of the energies and everything, all of the tracks. I think it hits like the 99% accuracy mark. This simple expression we've derived for the cross section. And in the ultra-relativistic limit, so when the energy is much greater than the mass of the muon, so in the ultra-relativistic limit now, one can show with a simple calculation that this cross-section actually goes to alpha squared over 4 ECM squared. And if you just take this limit, you get 1 plus cosine squared theta. Which I hope you guys are going, oh, because this is exactly what we came up with week 1. So you just work out all these terms, let E be really big. So let's just do it now. So when E is really big in this term vanishes, right? Because this fraction is really small, you're left with a 1, you just work out all of that. And you just get this fraction, expression. And this is what we did on week 1. So if you just make heuristic arguments, you get an amplitude in the ultra-relativistic limit. Pretty cool. I think that's pretty cool. And we work through this. So We did it. We computed our first real QED amplitude. Yes. However, I cheated you because the very smart student, which you all are, will say, Kyle, what about polarization? Oh, I didn't tell you anything about the photon's polarization. Actually, honestly, it doesn't matter, but it does matter in some situations. So next week, we will start with looking at the helicity structure, right? Polarization has to do with helicity. So we're gonna do this calculation. It's shorter, don't worry, it's not as long. This was, see, now when I say the QED calculations are long, this calculation took us an hour. You know, this is a long calculation. So next week, here's what we'll do. We'll do the helicity structure, and we will talk about helicities, which is not very hard. We'll talk about Mandelstam variables, right? So we'll talk about the U channel, the T channel, the S channel, the different channels. And we'll talk about something called crossing symmetry, which I hope you've heard about, because crossing symmetry allows us to use some of the symmetries between particles and antiparticles in our calculations. So today was a good first day of QED, and I hope you can appreciate how close we got to the. See, so when I said in week 1, I said we're 90% there. We're pretty close. We were off by a few correction terms, but in the lab, I assume none of you have wanted to be experimenters, but if you wanted to be experimenters, you would be screaming at me, and you would say those correction terms are very, very important because they'll get like the mass of the muon off by like 5 factors of 10 or something crazy. So they're important, but we came pretty close. This is the exact expression we pulled out. I'll make one more comment, then Johnson will enter, sorry. How did we make the heuristic argument in the first lecture? Well, what did we do? We used kinematics. We also used helicity arguments. We said, oh, here's a left-handed, right-handed, right. We did use helicity arguments. So maybe that has something to do with it, something to think about. Okay, anyways, anyone have final questions? Is everything okay? You're gonna have to work through that calculation again. It's not easy, so. Okay, I will see you tomorrow. Those of you that have questions in the morning at 9 and for our research group. And yeah, that's all I have. Congratulations, you have made it to QED. So well done. Okay, take care. I'll be sitting in Johnson's thing here and there too, so.
Yeah, let's take a 2-minute break before we start. So you guys can stretch.
I need a stretch too. Oh, Johnson.
Yep.
Can you stop the recording? I forgot to stop it before I made you host.
Yep.